So welcome back to the workshop. Our first talk today will be by Susanne Still from University of Hawaii, and she's been working on the relation of agency and thermodynamics for a while now. And today she will talk about thermodynamic efficiency and predictive inference. Okay, thank you, Susanne. You can go.
Thank you, Martin, for inviting me. Can you hear me loud and clear?
Yes.
Okay. It's always a little difficult to give these remote talks because I can't see the audience, so I don't get to see when people fall asleep.
And actually, she can see if she wants.
All right.
Yeah. Nobody's asleep yet.
My camera is sliding a little bit, so I'll keep adjusting it during the talk. So yesterday we saw a nice talk by Martin, who really thought hard about how to define an agent. And you know, there are many different ways to skin the cat. So you can take Martin's approach and say, I want to define where I should make the cut between the agent and the environment, or you can take the pragmatic view that many people take and just say that that cut is somehow given to you by the physics of the problem you're looking at, and then you have to model this agent somehow. And the thing I want to point out today, so this is just a silly sketch, right? In light of what Martin talked about yesterday, it's even silly to have this, but I guess one of the minimum things that there has to be for us to think that it's an agent is that it exchanges actions with the world, so it can do something on the environment, change the environment, and then it receives some data from the environment, so it can have some form of learning and adaptation going on. And the thing I want to point out today is that there are some generic restrictions on agents and that those have consequences. And in particular, we can use those consequences to get ideas of how we should be constructing learning rules for agents. So Martin spoke more about this yesterday, so I don't want to regurgitate too much of it. But I think that one problem with this goal-driven approach to behavioral learning or agency is that you have to choose what function you use to quantify utility. And on the same goal, you have to choose what function you will use to quantify the cost of a model, so the complexity or capacity of the model. And it's not always clear how to choose these functions a priori. And so you don't want to end up having just a descriptive theory, right? You want to have ideally a theory where you have complicated behaviors emerge from some kind of simple rules that you put in. So you don't want to have to go back for every behavior that you want to explain and go back and try to construct the objective function. You want to have some simple principles for these objectives that then in specific situations give you more or less complicated behaviors. That would be the ultimate goal, at least from a physicist's point of view, to describe these systems, these interacting and learning systems. And so today I want to highlight to you a physical approach. So the idea is that the laws of physics pose restrictions on agents. They can't process information infinitely fast, and at the same time it costs them no dissipation, and at the same time they can do it arbitrarily precise and with total robustness. That's not possible. There are these generic restrictions just set by the laws of physics. And so the idea that I want to follow here is then to say that if an agent is able to set things up for themselves, so to set their internal structure up in such a way that it would allow them, even just in principle, to reach those physical limits, then there would be no reason for them not to do so, because there is never a disadvantage for them to being able to process information faster or with less dissipation or what have you. This doesn't mean that agents always minimize dissipation, always maximize speed and all this. That's, I think, a very important distinction to make, because that would just be not true, right? There's plenty of examples in nature where living systems, for example, burn energy because they have to protect themselves for some reason. So this non-photosynthetic quenching is one example, where the plant just has to generate, like just burn a lot of energy. So maximize dissipation quickly to get rid of excess energy that would otherwise destroy it. So I'm not saying, you know, use the physical limits, optimize them at each point in time. I'm just saying, if you can set up your internal structure so that you could achieve them when you needed to, then there would be no reason for you not to do that. So that's the idea, and it's kind of important to me that you understand this idea from the onset, so that you don't get lost in the details that follow. So if you have questions right now, you should probably ask.
Anyone have a question? Yeah, you? No? No?
That's fine.
Martin?
No, it's good.
Question?
No questions.
Right. So then this implies kind of a long-term research agenda where I want to explore all the different physical limits to information processing. And I want to ask if some general rules for how to acquire and how to process information emerge from trying to come close to those physical limits in the sense that I just explained to you. And like I said, this is a long-term agenda. And for the moment, we will start with just exploring the thermodynamic limits to information processing. Oh, great, I managed to lose my slides here. Do you still see my slides? I moved my phone and it hit some key, and now I probably hit the escape key. I don't know. Do you see my slides?
Yeah.
Okay, they're back for me too. Sorry about that. Okay, so we will start by exploring simply the thermodynamic limits to information processing, and we will start small by just asking, what can we learn about general strategies for learning and adaptation? And those features are kind of central to agency, but of course, they don't include everything that agency can be. So this isn't the answer to the whole picture, it's just like a starting point. And I hope that you will find it inspirational, especially Martin, because Martin yesterday mentioned that he would like to be able to define agents through work and things like that. And I think this is what this talk might make clear, hopefully. So I want to summarize for you the insights, the things that I've learned from pursuing this research for the last couple of years, so that you get a big picture overview before we dive into the details. The main insight is that basically information that you can't use to predict contributes to dissipation. And because of that, predictive inference is the learning strategy that allows you to be energy efficient. And the fact that you see contributions to dissipation from this non-predictive information really comes from generic restrictions that apply to real-world agents. And in particular, we studied that they have to operate at finite times, and so these learning machines cannot remain in thermodynamic equilibrium throughout. And also, and this is the thing that I want to discuss today, these learners find themselves in partially observable environments. And that imposes structural constraints on the problem that contributes to additional dissipation in these information engines. You can then use this reasoning. So I'm trying to put like the problem of learning and adaptation here, I'm trying to ground it in physics. And you can then use this reasoning and extend this framework to include learners that can act. And I'll try to get to that towards the end of the talk. So these issues, the notion of information and entropy and so on emerged in the discussion about thermodynamics, and when people were talking about the foundations of thermodynamics. So I don't know how many of you know this, but in the old days, there was a theory floating around that heat is a substance. They called it a caloric. And they then moved towards that view that we have now, that heat has to do with the motion of these little particles that are there. So that wasn't clear from the onset. And at the time when Maxwell and Tate and Thomson and Clausius lived, they were moving from this caloric view over to the more kinetic view. And so many of you may have heard about Maxwell's steaming, which is basically the first time when this notion occurred that the statistical description of thermodynamics has something to do with information, or the information we know, or the information we assign to a physical system. And so Maxwell conceived of this container that has two chambers and a little dividing lever, something like that. You see the thing that the cute little demon holds there. And the idea was that if there was a very observant, neat-fingered being, this little demon, that could see the velocity of all the molecules and could manipulate this little trapdoor without expending any work, then it could sort the hot from the cold molecules. And thereby it could create a work potential without ever having to spend any work. And so this little conundrum has inspired many people. It started a couple years after Maxwell formulated the idea. One of the first people to try to build an automatic demon was Smoluchowski. That it didn't quite work out. And then Szilard in 1929 came up with a really brilliant contribution that we will learn more about in a minute, where he replaces this demon with a mechanism. And that's an important step, because then we don't have to think about the physiology of the demon. And this inspired lots of people, including Landauer and Bennett and many others. And
Susanne?
yeah?
Did you show a slide with a demon on it?
No, I'm coming to it. I want to give a little bit
Okay,
of
good. I was just wondering.
The demon, we look a little bit at the history. I can keep it short, but I thought it was entertaining.
Yeah.
So Szilard also inspired people like von Neumann and the cyberneticists. And so a lot of this really happened in the 30s, and it was kind of at the foundations of computer science, foundations of cybernetics. You know, these people, so Wiener ran these Macy conferences, these famous Macy conferences, and in turn inspired people like von Förster, and von Förster inspired Maturana and Varela and so on. And so probably many of us in the room here today are also inspired by this work. And among other things, specific studies of certain neurons in the brain brought forth the first neural networks. So this is the McCulloch-Pitts model. And although that's been refined a lot over the years, some of the basic ideas are still in use. And this also inspired the first physical learning machine. This is Rosenblatt's perceptron, to which Novikov then gave the convergence theorem. And this really got some mathematicians, especially in Russia, involved in the problem. And as you probably all know, Vladimir Vapnik realized by studying this perceptron problem and this classification problem, he realized that empirical risk minimization in general is not consistent without further assumptions. So you need to put a restriction on the capacity of the model class that you use to explain your data. And this was an important breakthrough, and in some sense allows us to formulate machine learning the way that we know it now, where we can say that basically machine learning is a form of empirical inductive inference, where the most ambitious formulation of the problem would be what parametric statistics also has been trying to solve all along, to go from empirical data to underlying laws. And this, of course, is different from the ab initio calculations that we like to do in physics, where you do exactly the opposite. You go from the known laws to the specific predictions. But one of the reasons why I think this machine learning is interesting to physicists is because we have to find the laws before we can use them. And so this is it's kind of a core question of human existence. Like, how do we figure out those laws? How do we figure out the structure in the world around us? And machine learning often solves the simpler problem, where we skip finding out the underlying rules and we go straight to prediction. And this might also be a strategy used by living creatures to survive. So this brings us back to the usefulness of a model and its cost, and the central question here, which is how should we design a general strategy to map data to some kind of memory, where with memory I mean representation of this data that is stable over certain time scales. So equivalently, we could have said, how shall we choose this objective function in learning? And so the view I want to take here again is that information is physical. There's real, tangible physical advantages to keeping smarter representations of the data. And so we want to ask if we can derive a strategy from a physical argument rather than from a statistical or philosophical argument. Typically, we use arguments like Occam's razor. But here we want to ask, can we get it straight from a physical argument? All right, so now we get to the Szilard box. And to get there, we're going to skip the daemon and go straight from the work that inspired Kelvin and Clausius and all the others that were the founders of thermodynamics. And this was work by Sadi Carnot. And so you probably all have heard about the Carnot process, right? Is there anyone in the room who hasn't? I thought not. And so I'm going to take you straight from the Carnot process to the Szilard engine, skipping all this discussion about the daemon and the erasure, Landauer's erasure and all this stuff, because this is a long literature and very controversial, and you don't need to go into all the details to understand the main issues here. So I have set for myself the unpleasant task of having to remind you of the Carnot process. Not my favorite subject. There you go. Here is the Carnot process as you typically see it in a textbook. You have two overall sections, one where you put work into the engine, one where you get work out of the engine. And
Susanne?
yes?
Okay, now you say, do you have a slide with the Carnot cycle?
Yes, it's not there?
No.
I'm looking at it. Which one are you seeing? You're seeing skipping the...
We see the one that says start with.
Oh, so you missed all those slides.
Yeah.
Well,
we.
No.
I mean.
That's
Okay.
weird.
So maybe when I asked, that's why I once asked about the daemon, but I guess you didn't have a slide with the daemon, but you did have a
I
different
have
slide.
lots of other slides. Let's
Okay.
scroll through them real quick. How can we fix this?
Maybe share the screen again. Try. I'm probably, I don't know.
Do you see it now?
We are actually somehow, yeah.
Now we see summary of insights.
And start with.
Now we see start with.
Okay, you didn't even see the most important slide. Well, that's kind of a bummer, isn't it?
But it always stay on the. I mean, in
Okay,
the
can you-
previous code, it always stay on the service. Is it?
Can you go forward and backward a few times with the slides just to check?
Backward,
Yes.
forward.
Just to check if we are actually seeing the changes now.
Yeah, I'm going forward and backward.
And
We're
now-
still at summary of insights. We didn't
And
see any change.
backward, forward.
Okay, it's stuck. Why is it stuck?
I think it's not our problem. Maybe the screen sharing.
Can you? Okay, can you reshare the screen?
And
Yeah,
share full screen, not only the PowerPoint. Maybe.
Maybe.
Or just show the screen.
It's also possible.
So maybe.
Show the. It has an option. You can show the whole.
Oh, look, now my camera works. We fixed it though.
And if you want to just show this, it is also fine.
What?
What do you mean?
I mean, with this, without presentation mode, it's also okay. And yeah.
Okay, can you try switching the slides again? Now we see summary of insights.
It's not working.
Okay. So.
It's working.
Can you? What if you don't go to the full screen, to the presentation mode, and you stay in the?
Oh,
Stay in the PowerPoint interface.
Yeah, try to change the slide there.
Interface. Yeah, this works.
Because this we see.
Yeah. And if we don't go to the presentation mode, then it's fine.
So now we see summary of insights. Can you, yeah, so can you just click on the...
Displaying the entire slide, right?
Yeah. And if you go forward, backward, some... Oh. Okay.
Yeah?
Yeah.
And now if you go to the next slide, yeah, we see it.
Okay.
Maybe we go with it.
Yeah.
Yes.
Yeah.
Okay.
It's good enough. Okay. Sorry about this.
Okay, so I guess we go through it again.
Maybe. I mean, maybe shortly. Yeah, quickly.
So the summary here, the most important insight that I've gained from this is that the information that you can't use to predict contributes to dissipation. And this means that predictive inference is the general strategy that allows you to be energy efficient. And these contributions to dissipation really show up because of generic restrictions that you have on real-world agents. One of the ones that I've studied is that they have to operate at finite times, and so they cannot stay in thermodynamic equilibrium throughout. Another thing that I want to talk to you about today is that they find themselves in partially observable environments, and this imposes general structural constraints on them, which again contributes to dissipation. These two insights kind of ground rules for inference in physics, and you can then use this reasoning to provide a general framework for learners that can act. Okay?
Yeah.
So let's see. So here was my slide on Maxwell and Maxwell's demon. So you see how cute that is with the little trapdoor?
Yeah.
You get the idea, right? The guy sorts the molecules. And then here's a slide with all these guys, all these amazing guys, like Szilard and von Neumann, Shannon, Wiener. They're the guys who started it all. And here is a slide with the neural networks and a picture of Pitt, tragic figure. And here's a slide with Rosenblatt and his perceptron, very nerdy looking, very cool. And Vapnik. Here was what I said to you about empirical inference, machine learning. And so this brings me back to the question I'm asking, which I want to answer from a physics point of view. And I think this is where we were. So now we want to skip the demon and go straight from Carnot to Szilard. So here we look at the Carnot process. You have two parts of the process that I put boxes around, one in which you put work in and one in which you get work out. And then each of these two parts, you can partition again into two processes, one in which you do an isothermal operation and the other one in which you do an isentropic operation. That's an adiabatic and reversible operation. And the isothermal compression or expansion you use to get work out at different temperature, put work in at a lower temperature, get work out at a higher temperature. And you use this isentropic compression and expansion to change between temperatures. So imagine you have your box embedded in a heat bath at a low temperature. So that's this blue stuff here. And you compress the box from some starting volume, which is below here, because the whole thing is a cycle, to some final volume V1. And then you pull the box out of the heat bath and you isolate it and you compress it further. Now, because it's isolated, it means that you heat it up because you accelerate the molecules. Then it's hotter, then you put it into a bath at the higher temperature, and then you pull out the partition and you get back to some volume V2. And then finally, you have to end on an isentropic expansion to get back to your original temperature so that you can run the whole thing in a cycle. Okay?
Yeah.
So here is an accounting of the work that you do during these steps in the isothermal steps. Because the average energy doesn't change, the work that you put in is the same as the heat that you dissipate here when you're putting work in, and when you're putting work out, you have to absorb heat from the environment, and that you can pull out in terms of work. And the work that you put in this isentropic compression cancels with the work that you do, the negative work you do in the expansion, because you integrate here from T to T prime, and here you integrate from T prime to T. So those two terms here cancel. And you don't exchange any heat with the environment by definition, because you've isolated the system. So the overall accounting just leaves you with a net work out. That's a combination of these two terms here that you get from the isothermal steps. And so the total work out you get here is this. These factors here have to be the same because of the adiabatic equation, which implies that the volume ratios here have to be the same, because you're heating to and cooling to the same temperatures. And overall, this is your net work out, and the efficiency, the Carnot efficiency, is then defined as the total work out, so this number here, divided by the heat that you absorb at the higher temperature. But the heat you absorb at the higher temperature is this here, the Q prime, yeah? Do you see my mouse?
Yes.
Okay, and so you divide this here by that. You notice that this is, the ratio is just mu, so that cancels this, and the K and the N cancel. The N is the number of molecules that you have in your ideal gas, and the K is the Boltzmann constant. And in the end, you're just left with the high temperature minus the low temperature divided by the high temperature. And you can write that as 1 minus low temperature divided by high temperature, and this is the Carnot efficiency. Okay. Now, I want to show you visually an equivalent process that's not so practical, but it's visually kind of nice. And I want to use it to get step by step to the Szilard engine. So here is the, in gray, sort of like blanked out, is the process we just stared at, right? Where I move from this V1 to this V prime to this V2 to this V. Now, I can move from the V prime to the V2 also in a different way. I could compress the whole box laterally, right? So I do my isothermal compression going from left to right here, and then I could squeeze my box laterally if I had a box that's squeezable in this way. It's maybe not so practical, but you could do it. It would be an equivalent process. And then when you do your isothermal expansion, you pull the thing out again, so you move it to the left. And then for the isentropic expansion, you could just expand the box again. And so here you've like pulled apart the compression of the gas and the expansion of the gas into 2 degrees of freedom, one which you only operate when you do these isothermal transformations, and the other one which you operate when you do these isentropic transformations. And I think it's visually nicer to see what's going on. That's why I'm showing it. Okay, so try to familiarize yourself with this picture and convince yourself that these 2 processes are equivalent indeed. Yeah, if you have questions, someone should let me know. Okay. So now to get to the Szilard engine, we're gonna go away from the ideal gas with n particles to a 1-particle gas. So when we are going to a 1-particle gas, here's our particle. We still have the same Carnot process here with my squeezing that I put in there, right? And now we can say, okay, let's replace this isothermal compression by just sticking in a partition in the middle. And this we can do without doing any work. We just slide in a partition into the middle here. And then when we're gonna skip this isentropic compression altogether, stay at the same temperature. So that's my blue here, right? The red is high, the blue is low temperature. We stay at the same temperature, but now if we know what side of the partition the particle is on, then we can just do the isothermal expansion and we can get work out of this. Isn't this fantastic? That is the idea of the Szilard engine. Now you have to realize that this will only work if we know what side of the partition the particle is on. And so basically we have to figure that out. So we have to measure and remember which side of the partition this particle is on in order to be able to do this isothermal expansion. And that was the large point, that we have to measure and remember this, and that this step must be dissipative. So now let's look at what an entire Szilard engine would look like, taking this step into account that you have to run a memory. So not only do you insert the wall, which costs you nothing, but you also have to measure and remember where is this particle. So you have to have some other system there that has two states, that tells you either the particle is on the left or the particle is on the right. And then you can run the isothermal expansion to get the work out. Okay? Now, how can you implement this? Well, often we like to think about these memories as some kind of bistable things, so like a particle in a double well potential. But the mind-bogglingly simplest way you can think about this, if you want to stay in this mindset of boxes and particles in boxes, is you can just have another box with another particle that you either compress this way or that way. And then you see that the step you have to take to measure and remember this particle location is equivalent to this isothermal compression you had to do in Carnot. So let's look at how the cycle would work, because once we've introduced another thing here, another box, a memory, we have to think about running that also in a cycle. So let's look at the whole cycle, and we'll do it for this right leg here, okay? So there's like two possibilities, right? But we'll just look at the cycle for the right leg. So we start by inserting the partition, and the memory is in some state that's undetermined. Then we measure and remember where's the particle by doing an isothermal compression on the memory. Then we do this isothermal expansion of the system, which gives us the work out. And then finally we pull out the partition of the memory here so that we're back in the same, in the initial condition, and then we can start the cycle again, put in the partition and so on. And so now we can, now we have a machine that gives us no workout, like the total workout is 0, right? Because those two contributions cancel exactly. But it's a way to, it's a concrete way to transform between work and information. And that's why people like the system, because it gives you a concrete model for how you can convert between work and information. And so here you see that you could have to put in KT log 2 because the amount of work that you have to put in has to do with the volume change here, and that's set to 1/2 because that's the optimal number. And you can pull out the same amount of work, and you can do an analysis of this and see that this is precisely the amount of mutual information you're keeping here in your memory. And so in general, you have, so you can do this reset of the memory also in the same step when you put your partition back in. So I've pulled these two preparation steps together here into one. And you see that there's one step where you convert work to information. And the more information you capture, the more you dissipate. And there's one step where you use this information to pull out work. Okay, the more information you have, the more heat you can turn into work. So I'm using a convention here that all energy flows into the system are positive. So minus W means there's work that you get out of the machine. Very good. So by now people can build these things. This is just one realization. So now I want to look at the assumptions that are built into this kind of information to work conversion scheme. It works for idealized systems. You can measure exactly the thing that you need to know in order to get the work out, so the relevant quantity. And if you can afford to move arbitrarily slowly, then you can achieve this limit. And if you can have complete control, so if you can actually change the things that you need to change. But these real world agents or learning systems don't usually, these assumptions don't usually hold for them. Don't find themselves. Somebody say something?
No.
Okay. They don't find themselves in this kind of state of total luxury where they can see everything they need to see, they can do everything they need to do, and they can take infinite time to achieve what they want to achieve, right? Usually there's a lot more pressure on us, unfortunately. Wouldn't it be nice if there wasn't? So real world learning systems typically live in partially observable environments, and they run at finite rates, and they have limited control. And so these are two things that I've addressed in my work, and this limited control is something I'm thinking about right now. And what I want to talk to you about today is this partial observability. Like what results do you get from that? What consequences do you get from that? So to make an example, now I lost my slide in here, okay. To make an example, let's construct a large box that's similar to what we just saw, but now we're gonna be mean. We're not gonna allow this agent anymore, or this observer anymore, to see the thing he needs to see. So here, this is the y position of this particle, right? Because here he can move the wall up or down. And so he needs to know, is this thing in the lower half or in the upper half in order to do his isothermal expansion. But we no longer allow him to look at the thing to look at this y position. He can only look at the x position of the particle. So then he can do nothing. On average, he can't extract any work. He can take a guess and get lucky sometimes, but some of the time he'll get unlucky, and then he'll do a compression to an infinite volume. And if he calculates what's the optimal strategy, he'll see that the optimal strategy is to do nothing. So he does nothing and he extracts no work. But if we make parts of this box inaccessible to the agent, so this dark gray here means, to the particle. This dark gray here means the particle can't go there. So basically I'm building a funny shaped box that looks like a staircase here, you see? And I can still move the partition up and down. Then I've included correlations between what I can see, the x position, and what I need to know is the y position. And now I can extract some work. And the reason I've chosen the staircase thing here is just so that it's easy for you to see the relevant quantities here, yeah? We'll see in a minute. But it's not a very natural shape. So maybe just a straight line would be a more natural shape, which would be also equivalent to tilting the partition in the original Szilard box. But I've chosen this shape just for simplicity of calculation. So you see then that the most informative memory that you can have is, of course, graining into 3 states. That tells you all, that summarizes all that you can know from the x position about the y position. And you see immediately that that's 2/3, that's 2/3 log 2. And so if you use this fully informative data representation to extract your work, then 1/3 of the time you learn nothing from the position, because the ball is in the middle, so you don't know if it's up or down, so you can do nothing. But 2/3 of the time you know where the ball is. You know, if you ever observed it here, then it must be in the lower compartment. And conversely, if you ever observed it up there, it must be in the upper compartment. So 2/3 of the time you can do that Szilard thing, and you can get your KT log 2 on average out. So this can give you at most 2/3 KT log 2 in terms of work, but you have to dissipate at least KT times log 3 to make your 3-state memory, your stable 3-state memory. So you can no longer achieve this bound of 0 for the dissipation. You have to be intrinsically dissipated from this structural constraint. And so you can ask whether there is a tighter and maybe more meaningful bound on dissipation than this number 0 that you have on the Szilard engine. And so as a hint, like I already told you, the relevant information that you have in the system is 2/3 log 2. And so you see that that's proportional to your maximum yield. And you can show that in general. You can show in general that it's the relevant information that sets bound on the yield, not the total information. And so because of that, the total dissipation is then bound by the remainder, by the irrelevant information. Now I can hear my echo. It's really disturbing. Okay, so to get to the general analysis, which I want to show you, I'm using concepts from non-equilibrium thermodynamics. It's far from equilibrium thermodynamics. Some people call it stochastic thermodynamics. And this is an emerging area that many of you are aware of, so I don't want to dwell on it too much. And really the one concept that I'm using for this is just this concept of the non-equilibrium free energy, so that you can assign a free energy to a non-equilibrium distribution. And the first place where I've seen that was in this little green book. But there's a proof I really like, and maybe, who knows, maybe some of the authors are even in the audience. That would be really awesome. This is a very nice proof. I really, really like it. Anyway, so the main insight here is that if you are in a non-equilibrium state, then there's an additional free energy that you can assign to this non-equilibrium state, and that is proportional to the relative entropy between the distribution with which you can describe this non-equilibrium state and the corresponding equilibrium distribution, which is the distribution that you would get if you stopped changing the external control parameters on this process, which are lambda of t here. If you stop changing them and you waited forever, then you would approach some equilibrium distribution. So this is the corresponding equilibrium distribution. And whatever you lose in this approach is basically additional free energy that you could have captured and turned into work if only you had enough information about the non-equilibrium state. And so this here is the main insight, that there is this additional free energy attached to a non-equilibrium distribution. You can then go ahead and add that to the regular equilibrium free energy to arrive in 2 short lines at your general non-equilibrium free energy here, which is the thing I'll be using. And this kind of stuff has been also experimentally verified. So even though it's been controversial, I think more and more people are feeling comfortable using these kind of non-equilibrium free energy notions. Okay, so now we're in a position where we can really ask the questions and where we can really try to go from information engines to strategies for data representation in learning. And so here I have made another sketch of a simple proto-agent. You see there's a work medium. The agent or observer can sense something and measure something, and it can do something to extract work. And all of these things, like what it can measure and what the work medium is and what it can do, so what the work extraction device is, all of these things are given by the physical setup. And the only degree of freedom here is in the observer. He can decide what kind of data representation he wants to use for his memory. So now we get to trying to derive what I just told you in words, that it's the relevant information that sets this upper bound on how much you can get out of an information engine if it's partially observable. So we will describe the whole system state, this is for the work medium, by this little variable z. And the important thing is that you understand that we could decompose this system, so this work medium, this gas, in our case it was this box where we can do the isothermal expansion on. We can decompose it into things that we can see or observe, our data and everything else. But we can also use a different decomposition into things that we can predict, control, predict and manipulate, and everything else. And together with this system that we can extract work out of, that we can use to absorb heat and get work out of, we also have a memory. And so we have 2 random variables here, the z for the system and the m for the memory. And the free energy is the average energy minus the entropy times the Boltzmann constant and the temperature. And so we're now going to look at these free energy changes during the isothermal transformations that we make on this information engine. And the free energy changes are, of course, the energy changes during a step minus the changes in entropy. We can then use the first law of thermodynamics, which tells us that these average energy changes are the average amount of work that flows into the system plus the average amount of heat going into the system to arrive at this formula. And we can then use the second law of thermodynamics. So from this formula, we can say, okay, the total work that we do on the system can never be less than the free energy change that we affect with that. That's one version of the second law. Or conversely, we see from this formula here that that means that the amount of dissipated heat, which is kind of the entropy change of the environment, together with the internal entropy change of the system, have to be non-negative. So the entropy production has to be non-negative. And if we use this formula here, we see immediately that in the memory making step, we have to counteract the internal entropy decrease by dissipating heat. And in the work extraction step, we have to counteract the amount of heat that we absorb from the environment by an internal entropy increase. So now all we have to do is calculate those entropy changes. And so the notation I'm using here is the entropy really is a functional of a probability distribution. So the joint entropy would be a functional of this joint probability distribution of the memory and the system. And I'm using this engineering notation where you write entropy like this. Probably all of you have seen it, so I don't have to dwell on this too much. So with this notation, we then see that in the memory making step, before we correlate the memory to the system, these two random variables are factorized. So the distribution factorizes, they're uncorrelated. But afterwards, they don't anymore. But the memory is constructed only from the observables. So all the things that we can't see don't contribute to the memory. So we have this distribution for the joint distribution, the memory making step. And so from these two distributions, we see immediately that the change in entropy comes out to be the negative amount of, so it's a decrease in entropy, and it decreases by as much information as we capture. This is our internal entropy change. The amount of heat we dissipate has to be larger than that. And conversely, in the work extraction step, we can only change the y component. We can't, anything we do on the system will not change the rest of the degrees of freedom. And the y component and the memory are correlated through the data, through this inference I'm going to make about the y from my memory. So I construct my memory from the data, but then I need to infer what is the value of the relevant variable. And of course, because they're correlated, I can make this inference. So there's then also a correlation between the memory and the relevant variable. And I'm using all of that up to get my work out. So I'm not, doing a partial extraction. I'm using all of that up. So afterwards, who are uncorrelated, this hasn't changed. And so you see that the entropy change is exactly the same as the information that I had about the relevant variable. Okay, so this is what limits the amount of heat I can absorb at the high temperature, how much information I had about the relevant variable. So now we can put this both together. So what happens in this memory making step is an old hat, right? Lots of people have thought about, there's a very nice review by Perron. Are you saying something?
Yeah, can you hear me?
Yeah.
There's a question. On the previous slide, there was a question by.
So in the upper part, you have the product of P of M and P of Z.
Yeah.
And then you have a P of M given X and P of Z, and then you end up with the mutual information of M and X. So I wonder if that P of Z is P of X or not. I'm confused between X's and the Z's.
I have to remember this 2 slides ago here. This is this. That's the important thing to realize, that you can decompose the system in 2 different ways, and they don't have to be orthogonal. You can write down all of the things that you can observe, that would be X, and then everything else. So I denoted that by X bar. Or you can compose it by all the things that you can predict and manipulate. So those are the controllables, I call them, and those are Y, and then everything else. And these are 2 different decompositions that you can make. So when I write down these probabilities here, there's a step that I haven't shown, where I'm writing, so here I'm writing P of M and Z equals P of M and now I'm using the decomposition of Z into X and X bar. So I have P of M, X bar. Then I say that's the same as the conditional of M conditioned on X, X bar times P of X, X bar. But P of X, X bar is just P of Z. So that gives you this. And then I look at P of M given X, X bar, and I use the fact that I'm only using X to construct M. And so the value of the things that I can't see has no effect on the probabilistic outcome of M, and so therefore it goes away in this conditional distribution here. Yeah, does that answer your first question?
Yeah. I think
Okay.
we got
And then
yeah.
for the other here, I'm using the other decomposition. So for the work extraction step, I'm using the Y and Y bar decomposition. And this is really an important point.
I also have a question with this these controllables. Do you have a way to construct them, or do you just assume you know them?
Yeah, so let me look back at the example to make this a bit more clear. So here, the controllable thing is the thing that you can predict. You can manipulate along this direction, and you can predict this variable here only up to this coarse graining. Even if you look back at the original, the large box, like even if you're allowed to see what you need to see, look, here. So even in this scenario here, you could make a data representation that's stupid, right? You could, you know, map this third onto, like you could do this three-state memory, map this third onto one state, map the middle onto one state, and map this state, this third onto another state. And it wouldn't help you. You would encounter dissipation. But the thing that you can predict here is only the coarse-grained value of this particle. Like if you, let's say you measure this to really high accuracy, and you use like a memory with 1,000 states. And so you can really remember where is this particle exactly. It doesn't help you, because in the time between when you made your measurement and when you're going to start your work extraction protocol, this thing can be anywhere here. So it's the putting in of this partition that sort of stabilizes the distribution that you can predict. So basically, when you stick in the partition here in the original Zillard box, what you do is you don't change the distribution of the random variable, right? What you're changing is you're introducing a hidden variable that if you discovered it, it would make it look at it as if this system is no longer in equilibrium with respect to the big box, right? And it's that hidden variable, basically, that's the relevant quantity that you need to discover. And so the features of this thing is that you can both predict it so that it's not just going away, like the information here would go away, right? So that in a sense, the distribution is stabilized. And the other feature is that you can then do something with it and change it, manipulate it in this work extraction step. Does that help?
I'm not sure, but I'll think about it.
Okay.
Yeah, we can talk about it later. Thanks.
Okay. So now we put these two things together. And like I said, the first step to make the memory, that's just old news, right? This is like the generalized Landauer bound. Lots of people have written about it in the last couple of years. There's a nice review article by Porondo and Sagawa and in Nature Physics from 15. But this step here is new, right? That you can't always reach the total information to work limit. You can basically only reach it if the thing that you see coincides with the thing that you can control, or the thing you need to know. So that's a special case. So in the more general case, where you just have correlations between the thing you see and the thing you need to know, you will always encounter extra dissipation here. So the lower bound on dissipation for this general, like partially observable engines, is then given by a difference between the total memory you suck up in your, or remember, and that part of that memory that is relevant, that you can use to predict the relevant quantity. So I've allowed for two different temperatures here, but if you say we're running all this at the same temperature, then this becomes very simple to verbalize, because then you can say, well, the remainder, if I take away from the total memory that part which allows me to predict relevant quantities, then I end up with irrelevant information. And so for isothermal engines, the dissipation is lower bound by irrelevant information. And this irrelevant information is a negative number. So this bound is tighter than the ultimate bound that we already know from the Landauer or general Landauer treatment of these information engines. Now, we can use this lower bound on dissipation to answer our question about how should we represent our data. And we can use it almost in a blindfolded way. So we can just minimize this bound over all possible representations of the data. And so the representation of the data is characterized by the stochastic map here from data to memory. And so we can write down an optimization principle by just plugging in this bound directly. So this is the Boltzmann constant. I can divide through by it. Doesn't change anything for the minimization. And then I can also divide through by this lower temperature here and end up with this temperature ratio, which is this alpha parameter here. And then for those of you who recognize it, this is exactly then the information bottleneck method. So you recognize this trade-off between having an accurate description of your data and keeping information that is relevant as basically a temperature ratio. And here is an example that will show you intuitively how this makes sense. So we go back to the staircase, the light box thing. And if we stay at the same temperature, run this isothermally, then we can do better than using 3 memory states. We can do better if we use only 2 memory states. And we have like a remaining uncertainty here, and we don't operate the box to the full extent, only partially. And then we can extract this amount of work, and we have to put in this amount of work, and overall the dissipation, the bound on dissipation is lower than if we use 3 states. But this changes as we change the temperature ratio. So you can calculate the temperature ratio by which this flips over, by which the 3-state memory becomes more efficient than the 2-state memory. And so basically the relative increase in cost that you have here doesn't outweigh the relative increase in gain unless if you extract at a higher temperature, and the temperature has to be higher by at least this much more. And then it starts to make sense to use a more detailed memory. So I would like to show you some demos of this process. But for this process then, you know, so here on the right, I have this process where I go between the low memory and the high memory. And again, I do it like in my first Zalaris slide with squeezing the box. So I don't actually lose any of the correlations between X and Y. And this process then saturates the bound, and it has an efficiency that is basically reducing the Carnot efficiency proportional to how much irrelevant information you capture compared to how much relevant information you capture. And so this is a quantitative thermodynamic measure of how much worse these information engines are, and it all depends on how the observer filters out the information. You can, now I would like to show you maybe the demos, but I would also like to get to this generalized framework. I don't know, do we have enough time for that? Martin?
Well, you can have 10 more minutes.
Okay, so you wanna pull up the demos?
Yeah, okay. Can you do it?
Can you play the demo on your side?
Can you play the demo from your side? I mean, we have it on the computer.
No, I can't play it on my side. You have to play it on your side.
1 second.
So while you pull up the demo, I'll continue, okay?
Yeah.
So you can extend this information bottleneck to a more generalized framework that can also include dynamical learning and interactive learning. So now the actions can come back in and we can treat agents. You can also generalize it to quantum systems.
Oh, back to the slide.
Okay, so we have the demo, so now you can just tell us which, but should we say a bit more on the generalized framework?
Where are the demos? I can't see the screen. Show me your screen.
Okay, let me share my screen.
Okay, we share our screen. Okay.
Can you see your demo?
Can you see the demo now?
Okay, so this is just the Carnot cycle. You can just run through it by like clicking clicking your mouse or something like that. It should run through the steps.
Yes.
Okay. So that's just the Carnot cycle. You see how the temperature changes. You see how you put work in, how you get work out. And the little yellow boxes are indicating our measurements. So we measure the particle is here or the particle is there. So this is the Szilard engine now. You have to click on it with your mouse to get to the next step. So it's kind of every time you click on the mouse, you see one step of the Szilard engine. Can you click?
Which one?
Click your
I already clicked.
He says he clicks.
Yeah.
that's
Should
strange.
something more happen?
Just click, I mean, just like
Anywhere
hit
on the screen?
your spacebar. Hit your spacebar.
Spacebar?
Spacebar. Okay.
Is it? Yeah. Is it? Did it change?
Oh yeah. Of course.
I guess there's
This
some
wall
problem.
squeezing.
What?
Wall squeezing, it says now, no? So that's the next step.
Okay, I'm not seeing it on my screen here. I am not. I'm still okay. So this isn't really working. But if you go through it, like there's movies 3 and 4 are demos of this partially observable Szilard Carnot process with 2 or 3 memory states. So I don't know if people are interested in it. You can share the demos with them later. Yeah, they're online. So
Okay.
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 Yeah.
The links. Okay, yeah, okay.
a modified engine and so on.
Yeah.
I just thought it would be easier to understand it if you see a little movie, you know.
Okay.
Okay,
Yeah.
so let's get back to my talk so I can get through the rest of them.
Can you share your
Then,
screen?
okay, can you share your screen again then? Yeah.
How?
Can
Just the same.
with the green share screen button.
Okay.
Yeah,
good.
yeah, okay, we see it.
Okay, so I hope that this has given you an idea of how you can put the task of learning into a framework that's rooted in physics and thermodynamics in this case, and then you can use that framework and extend it. And so we've extended it to dynamical and interactive learning. We've used it on reinforcement learning. We've done a quantum generalization. All of the things, for example, the thermodynamics of prediction, for example, also holds for quantum systems. This is something that Arne Grimsmo showed. And then together we extended the information bottleneck to quantum information bottleneck method. And when you think about these actions, then you're in this case where like Martin told you yesterday, where you have basically a bipartite system. And so you have to study the thermodynamics of strongly coupled systems. Also, for this bottleneck framework, you have to think about how can you learn from finite data. There's still like a step that you have to take because the original bottleneck framework just kind of assumes that you know the joint probability distribution between the thing that you can see and the thing you need to know. But you can also learn that from finite data. So I wanna put some emphasis on this here, this interactive learning, and then the thermodynamics of the strongly coupled systems in the last couple of slides. So if you use this generalized information bottleneck framework to model predictive inference in the presence of interactions, so in the presence of when the learner can change the thing that it's trying to learn about, so it can change the world, it can change the environment, it can change the things that are relevant quantities in the future, then you find that the learner has to balance between some form of control or exploitation of the world, and on the other hand, exploration. So not to get trapped in states where basically it doesn't see the entire state space, and which are not optimal because then the predictive power goes to 0. So that's interesting. And so this generalized bottleneck framework also contains some rather large theories as special cases. For example, it contains all of Crutchfield's computational mechanics, or the core elements thereof. And you can also use the interactive scenario to extend this to an interactive problem. So for example, you can define a causal state partition that's dependent on your action policy, and maybe you can classify policies by their causal effects, or you can classify them by their dynamical effects on the world, because when you're interacting with the world, you enter into you turn yourself together with the world into a dynamical system, and then you have questions about, what kind of scenarios can you learn, when are you chasing your own tail, things like that. So you can use this framework to address these questions. And a lot of that is work in progress. Here's a super simple example where you see this trade-off between exploration and control. You have two states, two states and a probability of leaving, and then you can set the probability of leaving as you wish. That's your choice. And so the optimal sort of like clever random policy is to set the probability of leaving such that you have control over where you are, but you're still visiting all the states. And that's different from just choosing a random probability here. And so you can show that this optimal clever random policy emerges from this kind of information-theoretic framework that I've shown you. Whereas if you just optimize some naive thing, for example, if you just optimize the mutual information between the future and the past, then you don't necessarily get that. Okay, so like I said, you need to think about the thermodynamics of strongly coupled systems if you really want to do a thermodynamic analysis of these agents. And Gavin and I have worked on this for a while, and we realized that some of the descriptions out there in the literature pose fluctuation theorems where they basically use a process in forward time that's coupled and use a process in reverse time that is no longer coupled, where they basically freeze one part of the process and play it back in reverse time this way. And if you don't do that, but instead you compare the forward and the reverse time processes that are like completely co-evolving, then you find that you can write the second law locally, and you find that the important term that kind of like controls the dissipation that goes between the two systems contains not only the transfer entropy in forward time, but also in reverse time. So you have to be a little bit careful when you do this analysis on what you take as your reference system, I think. And to fully apply this kind of analysis to agent systems is something I'm working on right now, and you still have to do the thing that Martin said yesterday. You still have to make some sort of a cut between what part of the accounting do you assign to the agent's energy storage and what part do you assign to the world's energy storage. So in some sense, the world puts in some energy, gives you a work potential. In another sense, you can also, look for states in the world where that work potential is higher, but you also have to put in energy to create your states, to make your memories and so on. So you have one part of the total energy exchange happens sort of in your local battery, and the other part happens in a battery that's supplied to you from the environment, and you have to cut that. And that's not necessarily entirely trivial. So it's still work in process, and yeah, it's great if more people wanted to look at these problems. So now I can conclude that, in conclusion, there are some thermodynamic limits on agency. Basically, I've shown you that there are limits on data representation, and that these imply that there are some optimal information processing strategies. And this is, if you want to be energy efficient, then you have to retain relevant information that allows you to predict the quantities you need to know, and you have to discard basically irrelevant bits. And you can use your actions. They are completely context dependent, but they will have thermodynamic consequences. You can either use them to find states in the future that have increased predictive power, or you can use them to exploit that work potential. And there's in general some trade-off between those two things. And you can also think about combining those two strategies into action sequences. And then you can ask yourself whether your dynamics of this combination ought to be in some sort of like impedance match with the environment. And maybe you can classify action policies by the effects that they have on the learnability of the environment. So as you're changing the environment, is it asymptotically possible to learn it or not? So those are all things that I'm exploring right now, questions I'm exploring right now. And another interesting insight is that also relations that describe the thermodynamics of strongly coupled systems basically follow in a few lines straight from causal intervention. And I want to end on that note and thank the Foundational Questions Institute for putting enough faith in me to fund this research. And then I want to thank Rob Shaw for making those demos that you can look at later, and all of my other collaborators who have contributed directly or indirectly to this work and my way of thinking about it. So
Okay.
Thanks for your time.
Yeah, we're a bit over time. Maybe we take, if there's one question. Any question? Yeah, there's one.
Thanks for the talk, Susanne. Can you hear me? Just make sure.
I can hear you just fine.
Good. Because since you mentioned, let's say, some of these ideas as being extended to, controllability, I guess at the beginning of your talk, I was wondering if you had in mind already some interpretations, possibly of. So I'm thinking about observability and controllability in terms of what Ockham defined as these two quantities, these two matrices. Do you think there's a nice thermodynamic interpretation for these two ideas?
Yeah, probably there is, but I can't tell you the answer yet. For me, this is all still a work in progress.
Thank you.
So.
Okay. You could maybe take one more question because of the technical difficulties, if there's one. And my main question you already started to answer a little bit. So I found this, it was very, very interesting and inspiring. I have to read your papers, but if I wanted to find a way, like find a place to split the system, and I would say, okay, I want to.
Because there is too much echo. Like everything you say gets echoed several times.
Okay, is it better when I'm here?
Yeah, maybe.
Yeah.
Fine.
So my question is basically, if I was going to ask you where you think is the best place to split the system, would you say maybe is there a place where?
I have a hard time hearing you.
Oh, it's too bad.
I think you're asking where is the best place to split the system or something like that?
Yes. Yes.
Okay, yeah, so basically you explained yesterday really well your point of view, right?
Yeah.
And so it's a little bit I'm coming from the other direction, right? So your view and my view are kind of like going in opposite directions, I think.
Yeah.
So
maybe.
I'm assuming that a lot of the setup is given to me just from, like, I can have a physical description, and for example, the quantity that I can observe, the data I can see is given. I know what I can observe and what I can't observe, and also the quantity that is relevant is something that I can describe. There's something that I can describe from the outside. So maybe it's good if we go back to this one slide here. Let's go back to this. Can you still see my slides? This one silly picture I made here of this proto-agent, yeah? This one. So I'm assuming that there is a system that an observer can look at and manipulate somehow, and all these three things are just there. They're sitting there for the observer to do, yeah? And then the observer has only this one choice. And this is why I can ask a precise question. And I, as a modeler of this box, this information engine, which includes its own little observer guy, I can describe this box. So I can see what the relevant quantity is. Doesn't mean that the observer can necessarily see it. So like I said, this information bottleneck assumes that this correlation is known, but you can also learn it from experiences. So you could have a signal that lets the observer somehow learn this. But that's another question, and that's not a question I was addressing, right? I was just addressing the question, if I can model this whole information engine, then different ways in which this observer represents its data will encounter physically different amounts of dissipation at a minimum. It also depends on how you implement exactly this observer, how much dissipation you encounter, and how quickly you run it, and so on, right? But there's like a lower floor on dissipation that just comes from the structure of this map. And that's all I want to know. And so I'm comparing, like, how much dissipation do I see here, depending on how this observer figures out his map. And so if you look at the bound that I get here, where's the slide? This slide here, right? These quantities here, or maybe this slide here, these quantities depend on this data representation. That's also why I can find the optimal data representation here. It's because these two quantities depend on it. And so because these quantities give me the lower bound on dissipation, the lower bound on dissipation in this agent model depends on how does this observer represent his data, and this is all that I'm quantifying here. And so then maybe you want to solve a harder problem where you want to figure out, like, where should I make the cut? If I'm just given some like goop here, some like jello, and I don't see any structure, and I want to make a cut so that I can start to see this structure, how would I do that, right? So then you would have to work backwards, and you would have to say, well, I can define, you know, bipartite systems in different ways here, and some ways in which I can define bipartite systems, I will see workflow going between these bipartite systems, and then I will see these bounds on dissipation and so on, and maybe you can skin the cat the reverse way. I don't know, but I can imagine that maybe you could.
Yeah, that's, yeah. Okay, so let's maybe thank Susanne again for a great talk. Thank you very much.